Hello everyone, this is Fateh Lohar, Assistant Professor, Department of Electronics and Communication at Engineering College, Jalore. The e-lectures prepare for RT syllabus, antenna and propagation for 6th semester EC students. In previous lectures, we have discussed aperture antennas and aperture antenna design considerations. In this lecture, we will discuss Babinet's principles of antenna and we will discuss the horn antennas and type of the horn antennas. First, we discuss the Babinet principle. Okay. According to the Babinet principle, when the field behind a screen with a opening is added to the field of complementary structure, the sum is equal to the field when there is no screen. So, meaning of this line we can explain by the design example. Suppose this is the field with no screen. Screen means this is screens. This is infinite connector and aperture is represented as a screen. Okay. The meaning of this statement is that this is a complete screen and we cut some portion for PC, perfect electrical conductor. We cut the portion. This is cut portion is. If the electric field due to this portion, okay, this is this and electric field due to this portion. If added both of electric field, the equivalent field is represented due to the free space area without screen. So we repeat again. When the field behind a screen with an opening is added to the field of complementary structure, complementary means both structure. One conductor, infinite conductor, and other is aperture of the conductor. Both are the complementing each other. The sum is equal to the field when there is no screen. This is the meaning. So let us assume that electric field source Z radiate into an unbounded medium of intrinsic impedance and eta equal to mu by E root square. Okay, and produce a point P, the field E naught and H naught due to this unbounded electric field. Okay, the field produces E naught H naught and this is the intrinsic impedance. Okay, the same field can be obtained. Okay, the same field can be obtained by combining the field when the electric source radiates in a medium with intrinsic impedance and not in the presence of first. This is an infinite planar, very thin, perfect electric conductor with an opening as a aperture. Basically, this is represent aperture which produce at P point the field EE and HE. Okay. Due to this field as a aperture, this is the aperture, and due to this design, the electric field is E and HE, and this is the impedance. And second, a flat, a very thin, perfect magnetic conductor SA which produced at P. The field is HM and HM, EM and HM. So due to this perfect magnetic conductor, basically this is the portion of this conductor. So due to this, the field is EM, HM, and this is the intrinsic impedance. So combining of the both of the field, this is for the perfect electric conductor, or this is for the perfect magnetic conductor. By addition of this, the equivalent represent the E naught. This is the E naught is field due to the unbounded region. Similarly for H field, we got H naught. This represent the field due to the magnetic field due to the unbounded region. You can see this is the field equivalent to. So meaning of this, if the area of the both complementary, FE, FEC and PMC, then equivalent field is E naught and H naught. This is represented due to the unbounded field. Okay. Now we discuss for second thing. The field produced by the source in J can also be obtained by the combining of an electric source J radiated in a medium with intrinsic impedance. Okay, due to this. Okay. An infinite planar with very thin perfect electric conductor SA, and which produce the field P, HE and same field to this. And second thing, the magnetic source M radiates in medium with intrinsic medium impedance ND in the presence of plate very thin perfect electric conductor SA, which produce P field due to this perfect electrical conductor. So combining of this or this, it also equivalent to the field due to the unbounded region. So you can see this is the field due to the perfect electrical conductor or electrical aperture conductor. So equivalent is represent the E naught, and similar for the H naught. Basically this is the duality. So other thing we have example, the infinite metal conductor, we cut the apertures. Okay, this is the aperture, this is complementary of this. If apply the transmission line feed at the point A, B, and similarly we apply point A, impedance at the A, B, JS, and impedance of the in this line is JC. So the complementary represent equation JS JC equal to n square by 4, eta square by 4. Eta represents the unbounded region intrinsic impedance. Okay. So this is a principle of the Babinets. So a proof of the Babinets principle and its extension can be justified using the Broca extension. It can be so that by applying the figure A, that the skin and its complementary are emerged in a media with intrinsic impedance and have the terminal impedance JC and JC respectively. The impedance are related to this. Okay. Now discuss the horn antenna. Horn antenna have a lot of the application. In case of the radar application, basically the horn antenna have the high directivity and high gain antenna, and also have high power handling capability. So due to this characteristic, horn antenna can be used for the radar applications, long distance satellite communications. Okay, basically horn antenna also considered as a feed source for the reflector in case of the cassette gram reflector antenna. Okay, the simplest one of the simplest and probably the most widely used microwave antenna is horn antenna. Horn antenna is widely used as a feed element for large radio astronomy, satellite tracking, communication dishes found installed throughout the world. In addition to its utility as a feed for reflector and lenses, it is a common element of the phase array and serves as a universal standard for calibration and gain measurement of other high gain antennas. Its widespread applicability stems from its simplicity in construction, ease of the installation, versatility, large gains, and prepare overall performance. E-plane sector horn antenna. Basically, the horn antenna two type E-plane and H-plane. The third type of antenna is first type is E-plane, second thing is H-plane, and third type is pyramidal horn. Okay. The first is we discuss the E-plane horn. This is the feed waveguide. This is the waveguide. This is the flare of the E flare. Basically, this is the electric field. The meaning of the E-plane, meaning the E-plane sector horn is one whose opening is flare in the direction of electric field. Okay, basically the opening of the flare opening in direction of the electric field. This is the electric field direction. The opening is in these directions. So, due to this, you can analyze the electric field and magnetic field in Hz and Hx. This is the row. Radiation from the sector horn antenna. To find the field radiated by the horn, only the tangential component of the E and H field over a closed surface must be known. The closed surface is chosen to coincide with an infinite plane passing through the mouth of the horn. To solve for this field, the approximate equivalent of the section is used. That this is current density in y direction and this is in x directions. And Js is equal to 0 any conditions. This is the radiation pattern. Okay, 3 emission radiation pattern when rho equal to 6 lambda and b equal to 2.75 lambda and a equal to 0.5 lambda. This is a polar plot of the radiation pattern of E-plane. H-plane. H-plane, the flaring the dimension of the rectangular waveguide in the direction of H-plane. H-field, basically this is the A field. So A field must be in these directions, perpendicular to the electric field. So flaring the dimension of the rectangular waveguide in the direction of the H field while keeping the other constants form a H-plane sector horn shown in the figure. The analysis procedure for this horn is similar to that for the E-plane horn, which was obtained in the previous section. Instead of the including all the detail of the formulas, a summary of each radiation will be given as a radiation. The field radiated by the horn can be found by first formulating the equivalence current density Js and Ms. It can be shown over the pressure on the horn. Okay, this is the current densities on the horn instance. This is 3D radiation pattern where rho equal to 2, rho 2 equal to 6 lambda and A1 equal to 5.5 lambda and B equal to 0.25 lambda. Okay. This is a polar plot of the horn antenna for H-plane. Now we discuss the pyramidal horn. The most widely used horn is the one which is the flare in the both direction. Basically the flare direction in both E and H field as shown in the figure. It is widely referred to as pyramidal horn, and its radiation characteristic is essentially a combination of E and H plane structure horn. So the simplicity, the analysis, and to maintain a modeling that lead to the computation that have been so to correlated well with the experiment data. Tangential component of E and H field over the aperture of the horn are approximated by the this is E field and this is H field in Y and X directions, and the current density is Y and X direction is R, J and My. This is the complete textures of the horn antenna. This is flare in both directions, H and Y, E plane and XY. This is the E plane, or this is the H plane. This is complete pyramid, or this is the E plane characteristic. Okay. Second thing is H plane characteristic. This is 3 dimensions when rho equal to rho 2 equal to 6 lambda and A1 equal to 5.5 lambda, B1 2.75 lambda and A equal to 0.5 lambda and B equal to 0.25 lambda. Oops.